let's go ahead and count on having our first exam on the 26th. Okay? So that'd be 2 weeks from today. If we get finished with biomechanics and everything else we need, we'll just start on the next part, which you will not be responsible for. The exam is only over X-Phys and biomechanics. Okay? I've started a review sheet. Got the X-Phys part done, and I'll work on the biomechanics part as well.
That's in class?
I'm sorry?
And that's in class?
Yes, that is in class here, 10:30 to 11:45. Okay. Dr. Mbiki, Satya Mbiki, is going to be here on a week from today, and so I need to find out what he's going to talk about and see if we need to include that as well. Okay. All right, but today we're starting on the biomechanics part. When we did X-Phys, we were looking primarily, especially the beginning part, we're looking primarily at the cellular level. Okay, so we looked at what a muscle fiber cell was like, the parts of it, sarcomeres, actin, myosin, all those things, and how those work to create contractions. And now, so now we know how contractions work. Now we're going to look at bigger picture with biomechanics, looking at the muscular system and the skeletal system and how those two things work together to create movement. And physics has a great deal to do with biomechanics. So when you're looking at the science of movement as far as the muscular cellular systems, we are looking at those levers and how those work to create movement. Okay. So we look at just a little bit of history. How did biomechanics get started? You can look back to Aristotle. He was probably one of the first to look at biomechanical things, had written a book on the science of movement as far as animals goes, and studied movement in animals and how that worked, even some in humans. Closer to us, we have Leonardo da Vinci, who was in the 15th and 16th centuries. He was what we called a Renaissance man. And when you think of da Vinci, you might think of his paintings. Okay, well, yeah, he was a great painter, but he also was an inventor. He did science things like this. So he would. Nowadays, we tend to specialize. And even like we have scientists who specialize just in certain things, like biomechanics. Back then, they were broad. They had a bigger picture of things. They did lots of different things. And Da Vinci was probably one of the first of the Renaissance men. And these drawings over here, he made lots of drawings. And this is just one of his drawings that looks at, I mean, if you look at his drawings, we're looking at levers, how the legs work to make movement, how the arms are working. All of that has to do with biomechanics. And so he did a lot as far as the beginnings of biomechanics. Later on, this gentleman here, Alfonso Borelli, he's known as the father of biomechanics. He was in the 17th century. He really started looking more specifically at levers and how they work to create movement. And so he is known as the father of biomechanics. He looked at things like forces, center of gravity, and really was the first to look at muscular movement, looking at static and dynamic principles using physics. Then we we had these gentlemen, Mary and Maybridge. And really, Borelli, back in the 17th century, he did a lot to do with biomechanics, the beginnings of it. And then really not much happened until these gentlemen, particularly Maybridge or Mybridge, however you say it. He started using film to look at movement. And the story goes that either Mary or Mybridge or both of them were in a bar one night, and what you find is that a lot of good ideas about science things tend to happen in bars or places like that because people tend to throw out ideas. And they were having a conversation with some folks, and some of the gentlemen that they were talking with said, well, we don't know, like with horses, we don't know what happens when they're running. And some of them said, there's always a point where there's a foot of the horse on the ground. And Mybridge said, well, I have a way where we can solve this question. Some people were saying there's a point where none of their feet are touching the ground. Some of them were saying there's always a point where a foot is touching the ground. Mybridge said, I can help solve it. I'll video them. And think back, early 19th century, videos weren't not very good back then, so that was a big thing. So he took some videos of horses, and lo and behold, we see what we now know now is common sense, is that there's a point where all four of the horse's feet are off the ground. And this is the beginnings of using film to analyze movement. He did also a lot, he and Mary, did a lot just looking at regular people doing regular things. Here is a young lady picking up a bucket. And what is she doing as she is doing that, looking at her movement that way. And if you go online, this is just one of hundreds of videos they have of people doing regular everyday movements. Okay? So they really helped move forward the study of biomechanics, particularly analyzing movement. Okay, so why do we need to study biomechanics? Well, a couple of main reasons. One is to improve performance. Thinking about, particularly for us, maybe sport performance. How can we make people better? How can they throw further? How can they jump faster? How can they jump higher? How can they run faster? So trying to make them better at a sport performance, or just maybe better at regular everyday activities. Another is to prevent or treat injury. Many of you may be interested in physical therapy. Well, physical therapy depends a lot on biomechanical principles. What's the best way to lift in order to prevent injury? What's the best way to walk in order to prevent injury? Or what can we do if you already have an injury? How can we make it better? And in this case, maybe what would be some ways to maybe make a joint stronger so that the lever is stronger within the movement? Like, if you've recently had knee surgery and you're sitting in a chair, what can you do to strengthen muscles to make it better so that you can get up without having to rely so much on that knee? Or how can you make the knee better so that you can do better movements? Okay, so that's part of what we look at with biomechanics. Now, the two overlap. As you can see, it would make sense that some of the things you're doing to improve performance could then be used to prevent or treat an injury, and then vice versa. All right, so some basic terms. Biomechanics, I really like the second part of it better. The first is kind of whatever, I don't know what that means. The science of physical principles applied to biologic systems. Physical principles having to do with physics. biologic systems having to do with us, movement. But I like the second part better. Study of how the skeletal and muscular systems work under different conditions. Okay, under a condition of a heavy load, easy load, slow, fast, whatever the conditions are. Hurt, not hurt. All kinds of things. Within biomechanics, there's really two basic areas. One is called kinematics, and that's really what Mary and Maybridge were looking at. The description of the temporal and spatial components of movement. Description, simply describing movement. Temporal, and this would be good to write down because this is a basic term you'll find in a lot of different science areas. Temporal means time, timing. We'll look at speed, we'll look at velocity, acceleration. That has to do with kinematics. Spatial. That has to do with where is something in space. So the idea that Maybridge and Mary were looking at the horse's feet, is there a point where all of them are off the ground? That's spatial. Where are the body parts in space? In that case, where are the horse hooves in space? Okay. The other part of biomechanics is kinetics. And this is looking at the forces involved in movement. Forces, the object in this case might be you or me. The person could be the object. It could be a ball, a bat, whatever the case is. Something you're lifting. Gravity. Thinking about things like friction. Those things all have to do with kinetics. All right, so let's look at some kinematic things to start with. So we're looking at temporal and spatial components of movement, particularly looking at motion and how an object is changing its position in space. One part of kinematics has to do with distance. How far can I throw a shot put, a javelin? How far can I long jump? That all has to do with distance. That's part of kinematics. With elderly, how long is their step compared to what it used to be like? How high, right? Yeah. How high is their step compared to what it used to be? That's part of distance. Again, we're describing movement, but it has to do with distances. Before I was hurt, where could I take my arm? My husband has a hurt rotator cuff right now. It's like he can't come up here at all. So where is it now versus where should it be? Okay, that's distance or spatial. Speed is part of kinematics. How fast is something traveling? And speed has to do, if we're going to get an equation for it, speed is equal to distance traveled divided by the time it took. Distance traveled divided by the time it took. Now, hold on to that. We're going to do some calculations in a second. But let's look next at velocity. How is our speed and velocity different? You and I in normal terms, you and I might use the terms interchangeably, not in biomechanics. In biomechanics, velocity has to do with how fast the object moves in a particular direction. So, speed has to do with distance. Velocity has to do with displacement. Okay, one more time. Speed, right here, that has to do with distance, and that's part of our definition. Velocity has to do with displacement. Okay, now, let's skip this a second. Okay, so in speed, what we're looking at, speed has to do with distance traveled. All right, on this diagram here, the person is starting at point A. They're going to end up at point D. But in the meanwhile, it's like they're skiing. Going from here to point B, and then from point B to C, and then from point C to D. So, if we're going to look at the formula, okay, the formula for speed equals to distance divided by time. And by the way, the 3 minutes is the total time. That's how long it took. So it took a minute from here to there, a minute from here to here, a minute from there to there. That equals 3. Okay. So from point A to point B is how far? How far did that person travel? 180. So 180 meters. All right. From point B to point C is how far? 140. And then from point C to point D is how far? Should be 40, is that right? No, 100. Is that right? 40 to 140, yep. Okay, so that's 100. That equals our 420 divided by our 3, and that gives us 140 meters per minute. Okay, that's this person's speed. It's just distance, total distance. Now, if we look at velocity, velocity has to do with displacement. So all you need to look at is where did they start and where did they end up? Okay, so where did they start? They started at 0, point A. They ended at point D. How many meters is that? 140. And so you got the 140 to the right. It doesn't matter, but for our purposes, to the right. Divided by 3, that's 46.7 meters per minute. Okay? In biomechanics, those distinctions are important. So that's speed versus velocity. Speed just has to do with total distance. Velocity has to do with displacement. How far, starting point to end point, did you end up? Okay. So that's speed versus velocity. Now let's look at acceleration. The rate at which an object changes its velocity. So how fast does an object change how fast it's going, essentially? And there our formula is acceleration is equal to the velocity at the finish minus the velocity at the start. So finish velocity minus beginning velocity divided by That delta sign there means a change in time. I think that's a delta sign. Okay, thank you. So, velocity at the finish minus velocity at the start divided by the change in time. So, if we go to this, gives us some practice on acceleration. So, using our formula, velocity at the finish. They're starting here, and they're going to here. Here's their end point. Here's the beginning, here's the end point. Each of these is taking 4 seconds. So on this side, velocity at the end is 8 meters per second. So that's where you get this, minus your velocity at the start, which is 0, started at a dead stop. And you divide that by the time, total change in time, which is 4 seconds. So 2 divided by 4 is equal, 8 divided by 4 is equal to 2 meters per second. That's our change, that's our velocity. That's our acceleration. This is a positive acceleration. We're getting faster. Okay, this is positive acceleration. Over here, what's happening? They're getting slower. This is what we call a negative acceleration. So at the start, the start when we're timing this person, they were going 8 meters per second. And at the end, they're at a dead stop. So down here, the formula, velocity at the end, which is 0, they're stopped, minus their velocity at the start, 8 meters per second, minus the time, same time, that gives us a negative 2 meters per second. So they're slowing down at a rate of 2 meters per second. Okay. Oh, let's see. What if we did this? What if I'm going to back it up. Let's look at speed and velocity again. Let's say, here's your start, and this person is going to run from here over to this side of the gym, which is 25 meters, and then go back to that side of the gym. Okay, so they're going from there to there. And it takes them, let's see, 5 seconds to do that whole thing. Okay, so calculate speed, calculate velocity. Just do it to yourself. Everybody try it, see if you can figure it out. The speed first. Versus their velocity. Pretty fast, actually. So, if we're going to figure speed, what's the total distance traveled? 50. 50, and what are you going to divide it by? 5. So that gives us 10 meters per second. Like I said, they're pretty fast. All right, now, what's their velocity? Remember, velocity has to do with displacement. 0. So we went 25 meters this way, 25 meters this way. We moved 0 meters. 0 divided by 5 is equal to 0 per second. They had a velocity of 0. Okay. Again, it kind of doesn't make sense to us based on what we're used to saying, but in biomechanical terms, that's part of what they look at. Okay, for now, you just need to know basically that's how we figure it out. So, that's part of kinematics, just looking at speed, velocity, acceleration. We can also look at where limbs are in space, those kinds of things. Let's look at kinetics. Kinetics, again, has to do with the forces involved in movement. A lot of inexperienced coaches, they will tend to use and focus on kinematics. So they'll describe things about what's happening. So, for example, an inexperienced, or let's say a coach who isn't as good as a good coach, for a shot putter, they might tell them, well, you need to spin faster, or you need to move across the ring faster, or you need to what are we doing here? Yeah, you need to glide across the ring faster as you're getting ready to do your shot put. Okay, that's kinematics. That's describing a movement. Yeah, it tells me what I'm doing right, but what doesn't it tell me? How to do it, how to get faster. Okay, that's part of where kinetics comes into play. So really your better coaches, they're going to look not just at kinematics, but they're also going to get into the kinetics. How can I get more force? How do I get faster across that ring? How do I overcome gravity? Some of those things. Okay? So, force is the push or pull exerted by one object on another. We'll look at gravity. We'll look at normal force. Friction. All of those are forces. A push or pull exerted on one object by another. You might be the object, by the way. One of your questions for today's reading had to do with the characteristics of force. And here they are right here. You should have been talking about these 4 things. One of those characteristics is magnitude. How large or small is a force? If we look at this picture here, thinking of somebody kicking a soccer ball, it has to do with how large or how small the kick is involved in the force right here. The force involved in the kick here. Okay, so it could be a large, forceful kick. It could be a small kick, just depending on what is needed in the situation. Another characteristic of force is direction. The force could be a push or a pull. My husband and I were moving furniture this weekend. Sometimes we pushed furniture, sometimes we pulled it. Helps to have little gliders on it, which is reducing friction, which we'll talk about. Helped a lot. Could be forward, backwards, up, down, combination of all of those. Over here, if we look at our kicker, direction, looks like they're getting underneath the ball, so it looks like the ball is going to go up. We can see the arrow right there. Direction, it's going to go more upward and maybe forward some. There's a combination there. Point of application. Where is the force applied on the object? When we were moving furniture, pushing high versus medium versus low had a different impact on how easily a piece of furniture moved. just like here, where the ball and foot, where the foot contacts the ball, really impacts the direction. Okay, so the point of application here is affecting the direction. These are interacting. Now this last one is probably the hardest to understand, the line of action. Where does the force pass? Does the force pass directly through an axis of rotation? Okay. All right. So, an axis of rotation is where is an object fixed, and it doesn't have to be fixed so that it's not moving, it's just fixed in terms of where everything else is rotating around. Right now I'm going to fix my cell phone right there. There is where this is the axis of rotation for my cell phone. If I apply force directly on that axis of rotation, it's not moving. But if I apply force up here further, away from the axis of rotation, it'll move. If I apply it up even further, it will move even more and more easily. Just like, here's a ball. The ball is coming toward a batter, let's say, or a tennis player. US Open was on TV this weekend. Ball's coming toward the tennis player. It's coming straight here. There's no rotation to it whatsoever. The axis of rotation is right in the middle. Okay? If you apply a force directly flat on that axis of rotation, there will not be any rotation to this object. If I apply force above that axis up here further, you're going to get a rotation to the ball. The ball's going to move this way. If I apply it underneath here, you're going to get backspin. Okay, so your axis of rotation, right at the spot where you're not going to have any different kind of movement, essentially, just like with my cell phone. That helps to explain our different spins we can get. There's a guy. All right. Now, hopefully you remember Newton's laws. Newton, Sir Isaac Newton, he was kind of beyond the Renaissance people, but he was still kind of doing all kinds of things. He came up with these laws. You all know the idea of Newton sitting under a tree and the apple falls on his head and he comes up with these laws, and who knows if that's how it happened, but he's the one who came up with these laws. His laws explain the basic ways of how the effect of force acting on an object. How does force act on an object? And they had these basic principles. Hopefully you remember them from high school physics or something like that. Now you get to see how they work in terms of biomechanics, and even more when you get into your regular biomechanics class. We'll just look at a few things. First of all, we look at the law of inertia. A body at rest or in motion continues in that state unless acted on by an outside or unbalanced force. Ball is there. It's not going to do anything right there because no force is acting on it. If I take it, touch it like that, that is an unbalanced force compared to what the force that was right there causes it to move. What was the force that caused it to stop? What? Friction, good. Friction is a force that's working on between the object and this table. If I toss it up, that would be my force from my bicep and other things. It's causing the object to not be at rest anymore. That's an unbalanced force. And then it stops. and goes to the ground because of what force? Gravity. Okay. Well, this helps to explain some pretty neat things about some safety things, and also if you have a ketchup bottle, how that works and how you get ketchup out of that. So let's look at this explanation first.
Unless acted on by an outside force. This means that moving objects will stay moving and still.
Let me start again.
The law of inertia states that objects will maintain their state of motion unless acted on by an outside force. This means that moving objects will stay moving and still objects will stay still, unless you push or pull on them. There are two safety devices in your car to protect you from the effects of inertia. The first is your seat belt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion. The second safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Okay, so back that up. So you're traveling along in your car, and all of a sudden you rear end somebody. What happens is that the law of inertia states that a body in motion in this case continues in motion unless it's acted upon by an outside or unbalanced force. So the car stopped, it was in motion, it stopped because you hit another car. But your body wants to keep going, it's still going, and will keep going and will hit the dashboard unless it's acted upon by another force, which is your seat belt. Okay, that's why seat belts help to keep you safe. The idea behind the headrest is just the opposite. You are stationary in your car at that stoplight, not somebody else's fault. They run into the back of you, and your car moves forward. There's an unbalanced force moving on it, but your head wants to stay where it was, because your head's on a lever. And if your headrest is there, that will prevent it from staying where it was and will help it to move forward with the car, thus helping to keep you safe. Okay, so the law of inertia helps us as far as safety in vehicles. Now, think about this. Ketchup, twisted peppermint, lotion, whatever the case may be, I want to get some out. And there's not very much in here. Think of a ketchup bottle, and you've all done it. What do you do to get the ketchup out? What do you do to get the little bit left in your bottle? What do? You whack it down, okay? What are you doing here? Who could explain that? How is the law of inertia being used to help get that ketchup or that lotion out? Yeah.
The container comes to a stop with the contents. Keep it.
Exactly. So my lotion is up here toward the top. When I make a hard, forceful motion down and then stop it, my container stops, But the lotion inside doesn't stop until it hits something else that will make it stop, the bottom of the container with your ketchup or your lotion. And now I can take it out and get me some twisted peppermint. Law of inertia helps us get ketchup out. Gets lotion out. So, very important as far as movement goes. Now, let's look at another law. The law of acceleration. An acceleration of an object is dependent on the force acting on the object and the mass of the object. That's the one I was thinking of. So we had the definition, we had the formula for acceleration. Now we're looking at things that affect acceleration. Acceleration depends on the force acting on the object and the mass of the object. Okay? So here's our formula. Acceleration is equal to force divided by mass. That formula there, what does that tell us about the relationship between force and acceleration and mass and acceleration? If we double the force, what's going to happen to the acceleration? It will double it. Okay? What happens if we double the mass of the object? The acceleration halves. Okay, so there's a positive relationship between the force placed on an object and its acceleration rate, but there's an inverse relationship between the mass of an object and its acceleration rate. Okay, let's take a look at this. So, let's say you have a brick. Say I had a brick up here. Right here, I put force of my hand and move the brick. Okay? Second picture. Now, if I take two hands and double the force I'm putting on my brick, I've now doubled my acceleration. But if I take two hands and double the mass, now my acceleration at the bottom is the same as at the top. Okay? Over here, same idea. What they're showing you is that with a small force, you're going to get a small acceleration. With a larger, double the force, you're going to get double the acceleration. Okay? So that's another one of Newton's laws. All right, now the next one, the law of action and reaction. For every action, there's an equal and opposite reaction. Got an action, there needs to have an equal and opposite reaction. The third of Newton's laws. Right now, all of you, as you are sitting in your chair, you are exerting a force on the chair. But at the same time, the chair is exerting a force up on you. There's an equal and opposite reaction. Okay? We didn't have one here. It's a bad example anyway. In your book, they talk about how if you have a chair, let's say this was all tile, not carpet like it is. And I had a chair here. And I stand on the chair. Say it's a chair like what is back there. It's a movable chair. It's just a regular chair. And I'm on tile, remember. Okay? And I go to jump off of the chair. What's going to happen to me? What's going to happen to the chair? Chair will go backward. I will go forward. Hopefully I won't fall. That could happen too. But what's happening is, as I'm pushing off of the chair, at the same time, the chair is pushing, I'm pushing off on the chair, and that's causing the chair to move backwards. Meanwhile, the chair is pushing forward on me, which causes me to go forward. And that's the action. There's an equal and opposite reaction. Now, from here, what if I'm standing here and I jump forward off of the ground? Do I go forward? Okay, I go forward. What happens to the ground? Does it go backwards? No, how come? The mass is too big. Okay, the mass of the ground, which is the whole Earth, is pretty big. And so it's not going to cause the ground to move. But I will go forward. Okay? Now, that has to do with our mass. There is not an equal and opposite reaction here because my pushing wasn't equal to the amount of push that the Earth is giving me. Does that make sense? Okay, so there isn't an equal and opposite reaction. Okay. Now, these come into play a lot when we're doing movement, and we can use these various things to help us move better. Okay. All right. So let's look at how force and motion are related to each other. This is Kelvin and Hobbes going downhill, illustrating momentum. What we see here is the impulse-momentum relationship. This is very important to a lot of areas in sport, in movement in general. Force times time is equal to mass multiplied by your velocity, change in velocity. For every action, there is an equal and opposite reaction. Here's an action, here must be an equal and opposite reaction. Impulse is this part of the equation. Force times time, the product of force and the duration of the time that the force is applied. Do this. So here's a chart you might want to copy down to help you understand the relationship between force and time and impulse. Etc. So what we're seeing here is that force and time, when we look at, if we want to keep impulse, or if we have to keep impulse constant, we can still change these variables. We can change force and time, but so in the top case, if you have a force of 100, and then the time it takes to do that is 1, that gives you an impulse of 100. What if you want to keep the impulse the same, but decrease the force in half, what do? You got to double the time. If you want to make your force go down 4 times, you need to increase your time 4 times. And that'll keep the impulse the same. Okay? So you can do things to time to decrease the force involved in a constant impulse. Okay? Let me say that again. You can do things to time that will decrease the force that's involved in a constant impulse. Okay? And we see that in things like in sport. Well, we just saw it in a car, in the airbag, in an airbag. So driving along, and let's say your airbag doesn't work and you hit a brick wall. Okay? The impulse is 100. The time it took to do that was instantaneous, 1, and you hit the dashboard in a time of 1 second, let's say, and that was a force of 100. The airbag helps to protect you by increasing the time it takes for your head to hit something, which then decreases the force involved in that hit. Everybody see that? Your airbag is increasing the time. Let me give you a sport example. I grew up in South Dakota and in a very, very small town, and we had a tiny, tiny gym. Tiny gym. And in fact, when you're playing basketball, the out-of-bounds lines, you were lucky if you had that amount of space between the sideline or the end line and the bleachers or the wall. And let's just say the wall. I mean, literally, here's the end line. The wall was probably there. Okay? There's no space between there. Okay? So, what was on every end line? What was on the wall of every end line to help protect us? Mats, right? We had mats put up. How good they are, but we had mats put up. Mats are doing this right here. So instead of directly hitting the wall, which would give you a force of 100, because you directly hit the wall without anything in between here, what happens is that you are making it slower. You're actually hitting the wall slower when there's a mat there. That's decreasing the force, which is, the impulse is still the same. It's just spreading it out more, taking you longer to hit that wall. What are some other things, maybe equipment or things you do in sport to increase this time, which thus decreases the force? Yes?
Maybe like the gear that catchers wear in baseball and softball.
Exactly. Yeah, the gear that catchers wear in baseball and softball. That chest protector, even gloves in baseball and softball. That's the idea behind it. Nobody knows that, but that's the idea behind it. You are increasing the time it takes for the ball to hit the chest, hit their hand, whatever. It is making the force less. Right there. What else? Football helmet, exactly. The pads inside the helmet, that is helping to, instead of hitting, look at pictures of football helmets 80 years ago. You were pretty much directly just hitting. I don't know why they even had the helmet. You're pretty much just hitting the head. Now you've got padding in there. That makes the force less because you're increasing the time. What else? Yeah?
I would kind of think of the opposite. If you shorten up that time, like with bench press, a lot of people will put wrist wraps on.
Okay.
So they don't have give in their wrist, so you fill, a force you put out just goes directly into the bar.
Okay, good. We're gonna talk about that. That'll be a little bit different. Same idea. That's a good idea there, but we'll talk about it in a different way. What else?
Like a metal bat versus a wood bat.
Oh, yeah, that's good. He said a metal bat versus a wooden bat. Okay, and let's hold on to that because that's going to help us with our striking again, too. What else can you think of? Anything else? Yeah.
Can you like do tumbling your ball over the foam pit instead of like the actual floor?
Okay, yeah, you have your mats on your floor with your tumbling routines. That helps with cushioning, definitely. That's an excellent one. Okay, let's see. I had some other examples too. Airbags, baseball gloves, helmets. You got most of these. Gymnastic mats. In boxing, anybody boxers in here? Any boxers? Okay. In boxing, when you're ready to take a punch, some boxers, they have learned to ride the punch. So they know a punch is coming. They will move their head with the punch. What's happening is that they're increasing the time of the collision. And that then decreases the force that's involved. Watch boxing matches, Mayweather and what's his name. Might have something there that helped with that. Okay. Now momentum has to do with mass in motion, your mass times velocity. So let's say that I'm standing at the top of a hill and J.J. Watt is standing beside me, and we can run the same speed, probably not even close. I'm sure he's much faster than I am. But let's say we can run the same speed. And we both start running downhill. Who's going to have the greatest momentum? J.J. Watt, because he has greater mass. Probably at least twice the mass I do, not 3 times. So his momentum is going to be much greater. So mass impacts momentum. Keep in mind, the whole idea here is that if something changes in this side of the equation, these two have to be equal, so something else has to change over here. Okay? So that's what this is showing you. A change in an impulse causes a change in momentum. So I change this. If I change something over here, something has to change over here. If I change something here, something has to change over here. Again, make sure you understand that. For every action, there's an equal and opposite reaction. That's what this formula is telling you. If something changes over here in the impulse, something has to change over here. Something changes over here, something has to change here. Now, let's see if we can do some of these. All right, we're going to drop some eggs. All right, so what we have here, this is an experiment in which we could change the egg size. We're dropping eggs. We could change the egg size. We could change the height from which we drop an egg. We could change the landing surface. So you could have a small, large, or jumbo egg. You can drop from 1 meter, 5 meters, or 10 meters. It can be onto a hard floor, a 1-inch foam, or a foam box. We're going to look, to start with, we're going to change the size of the egg. So what are we changing? If we look back on our formulas there, what are we changing? If you change the size of an egg, what are you changing? The mass. Okay. So we're going to run a trial here. This is a small egg that's dropped from 1 meter. Everybody see the 1 meter mark? You kind of got to look here and here at the same time. So let's drop the egg. Here it goes, here it goes, here it goes. It's the ground. Okay. So the egg broke. The velocity change was 4.4 meters per second. Okay? So our force was 44 newtons. I think that's what that is. Now, we're going to change the size of the egg. So is the velocity going to change? How many think the velocity is going to change? How many think the force is going to change? And why is the force going to change? Because the mass is getting greater. Well, let's look. So we're doing a large egg now. Here comes, same distance, 1 meter drop, just a large egg. Our velocity was the same, 4.4 meters per second. But notice how the force changed. It went to 66, just because we increased the mass. Let's look at a jumbo egg. Here's the biggest egg. Here it goes. Da, 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 da. Down there. Still broke. Notice how, again, our speed didn't change because it's the same distance, but the force increased again. Okay, now let's do this. Let's go to the small egg, and let's run the trial again. This is from 1 meters. We're going to change the distance this time. So it's 4.4 meters per second. Now, what's going to happen as we go from 1 meter to 5 meters? What's going to change? The velocity will. Okay, so let's look. So look, now we're here. The egg will go faster. It's a little bit more fun. And there it goes. So if we look now, 9.9 meters per second. And our force increased as well, right? Should have. Okay. We go from here. Now we're going, starting higher. So you should see our velocity change. Watch carefully. There it goes. And we see that our velocity changed as well as our force. Force changed because the velocity changed. Okay. Now, the landing surface is what's going to increase our time of collision. So we saw what happened with the hard floor. Everything broke. Let's see what happens at 10 meters with the small egg and onto a 1-inch foam. Let's see if we protect the egg at all. It is fractured. Our egg is fractured. So not quite good enough. So that's showing us, yeah, you slowed it down some, but not quite enough. You slowed down the impact some. So now let's try the foam box. A little bit more foam. See what happens. And there, our egg is safe. So what we see is that there's some trial and error. That's what scientists do when they're working and trying to figure out ways best to protect athletes, like with the helmets and stuff. They're trying to figure out how much foam is good, how much is too much, and that's all biomechanical stuff, which is pretty cool. Now, if I can get out of this, there we go. Okay. Oh, now, we've looked at how you could decrease the force involved by increasing the time that's involved in a collision. And let's go here. So what if we looked at the opposite way? What if we wanted to help with hitting? So you want to increase the velocity, increase the force. So like swinging a tennis racket or hitting a baseball. What things could you influence? So you know how they always say that you need to follow through, like when you're batting or when you're hitting a tennis racket. Now, when you think about following through, what is happening in our relationship there? Look at the top formula there. What is being changed? The time is being changed, okay? So you would think the time is being changed. So what would you think would happen to the force? If we teach people all the time, kids all the time, you need to follow through. You're batting, you need to follow through. Don't just stop here, okay? But following through, if it increases the time, what would it look like it's going to happen to the force? It looks like it would decrease the force. But actually, that's not what happens. In that case, in following through, what happens is that the more time you spend on the ball with like your bat, what they find happens is that it goes to the other side of the equation. Force is just a product of how hard you're hitting the ball, how fast you're doing this. And what happens is that with following through, what you're doing is actually increasing the velocity. And that increasing the velocity then helps to equal out the force and time relationship, making it a better hit. Okay, so it's kind of, we've been looking so much at these two things together, but remember that if you change over here, you could still change things over here, and that's what happens when you follow through. So that's a little bit different than like our collision thing that we've been doing.
So overall, what it does is increase the momentum, which results in increasing force?
Yes. Yep, the momentum increases the force then. Yep. Even though you're decreasing the time, or increasing the time, yeah. Yep.
So the impulse, would you think of that as, is it directly related to, let's say, distance and throwing the discus?
Yes,
So
definitely.
The higher the impulse, the time and force, part of the distance is going to apply to it.
Yeah, and that's what you would want to work on, part of what you work on with the other things. Especially like people doing the spin or even gliding across in the shot put or discus. That helps, okay, that speed, okay. All right, oops. So, this would be a good place to stop. So we'll start with gravity next time and keep going with our biomechanical stuff. Don't forget you have an assignment due